All right, welcome everyone. Can you guys hear me? Make sure everything is working.
Yeah, we can hear you.
Perfect. Awesome.
I totally thought that said today's donuts.
Today's donuts. That would be nice. You're welcome to have some donuts during class. No, these are documents. Yes. Well, great. Nice to see all of the black screens. We had a day of people showing themselves, so that was great. But if you are someplace where you can turn your screen on, that's awesome. I would appreciate that. If you're someplace where that's not possible, don't worry about it. But great, awesome. Welcome, everybody. Okay, well, I hope classes are going well so far. 1 week in the books almost, so that's good. So the plan today is to just keep on working with our making sure that we've got a background to pick up and begin working with our this semester. So just some of the things that we talked about last time were like our markdown, how to add R code to our markdown files, how to add text, how to format it a little bit, import packages, data types, data structures, and that sort of stuff, how to assign things to objects, and adding comments to code and all of that sort of stuff. Were there any questions that anybody has about anything we talked about last time? Is anybody having trouble finding things for the class in Canvas, or anything I can help with that? Good. Okay, so then the plan today is to work with a couple of documents. Let me share my screen. I have no idea what you're looking at right now. Let me try that again. This is what I wanted. Okay. So hopefully you're looking at like a browser. Does that look right? Good. Okay. I was telling my colleagues how I feel like I forgot everything on Zoom after class on Tuesday. I couldn't find like pull button and all this other stuff. So I sat down and did a refresher with myself yesterday. So good. Glad you're looking at this screen. The materials that we're working with today are down here in Thursday materials. Which is, I made it kind of a nicer formatted worksheet sort of version of the stuff that we're going through. Depending on what you prefer, you can open up this document, which is a PDF, which is not interactive, obviously. I would also, if you've got R open, I would just encourage you to open up that same file that we were working with last time, since that has some of the code blocks in there that you can work with. But you don't need to open that document. If you can just open up an RStudio window, that should be enough as well if you don't want to play around with that document. So I'll be kind of jumping around today. At some points, we'll be working with this R markdown file. At other points, I'll just be kind of annotating a PDF. Okay. Is anyone having any trouble with those documents? I believe I can drag them into the chat as well. Okay, then I will share the PDF version of this. And again, if you want to work with the R markdown file, go for that as well. Okay, so just kind of picking up with where we left things off last time. So in case you're kind of curious, like this whole document was created in LaTeX, which is what we use a little bit with in my math lab. And so there's kind of this trade-off, like you can't format things as nicely in our markdown, but the code you can run and the code looks nice. When we're kind of LaTeXing things, it's the reverse problem. We can make everything else look nice, but sometimes the code is going to look a little bit weird on these documents. So for example, you should see like this has a little, space thing over here. That's not actually a character that you would type and that sort of stuff. Okay, so last time we talked about kind of different different data types, 6 of them over here. And in particular, I think one thing that you want to watch out for is when we're dealing with numeric data, that could be decimals or that could be integers. Typically, we're using decimals, we're measuring things, but sometimes we're counting things, right? We're working with discrete distributions and we might be working with integers. If you're ever unsure, like what sort of data type and something is, then you can use this type of function in R and it'll tell you what it is. So like the output of this would be double, right? It's gonna be one of these 6 things. It's gonna tell you what sort of output it is. So when you do this, it's gonna tell you integer versus character over here. And we'll talk about how we might want to work with categorical data today. Be a little bit careful about how we set off the data types for categorical variables differently than how we do it for characters. And this command is numeric. This is like a logic function. So the output of this is going to be a true or a false, depending on whether the input is numeric or not. So for example, this would give me a false because clearly that is not a number, whereas these two would both give me trues because remember this L over here is not like a character L, but it's denoting an integer. Any questions? Okay, and we also talked about these data structures last time: vectors, matrices, array, data frames, and lists. And I think one important thing to keep in mind here is the top 3 are homogeneous, meaning we can only store one data type in each of these. So everything has to be an integer or everything has to be a character string. In these cases where data frames and lists can involve different types of data in the same, stored in the same object. So for the plan for today then is to talk about all these different data types, largely data frames and arrays, and talk about, oftentimes we're working with data sets that are already created for us, and we're going to be doing some exploratory analysis on them. But sometimes we're going to want to create our own. So I want to talk about how we can create vectors and how we can slice vectors and arrays and data, extract like subsets and filter out parts of the data set that we want. And I will just say that, that R is like incredibly robust. So if you are like feeling like, man, I don't feel like I understand R because I don't know how all of it works. Nobody knows how all of it works. So don't worry about it. I know like the little tip above the water myself. So there's just so much stuff that you can do in R. So my goal here is not to have you come out of this class knowing how to work everything perfectly in R, but at least knowing like what are the possible things that I can do. So pretty much anything that you probably can imagine needing to do is possible in R. So we're just trying to get the foundation going here, but not an exhaustive treatment. Okay, so the most common way of setting up vectors, if you're generating them yourself, would be to use the combine function or the concatenate function, which is just a C. So this means combine all of these things into a vector. Same with this and same with this. So this is going to create a vector. So notice that all of these things inside of here are the same data type. And oftentimes, right, we want to create vectors that have certain pattern to them, like the first 100 integers or something like this. And so you wouldn't want to type out, 100 things that are going into your vector. So there are some nice ways of generating pattern vectors. So my kind of thinking about things today is we're working with generally kind of small vectors. These are not things that we would need, you know, software to analyze. So we can kind of think about how these R functions are working just like on paper and not necessarily need to enter this stuff into R, but you're welcome to try it out. So let's just kind of think about what some of these functions might do. So any thoughts on what this sequence, and we haven't defined this, and you can kind of look ahead if you want, but I was thinking of just thinking about this first, and then we can define them on the next page. But what do you think this sequence function would do here? Sequence 1 through 10.
It'll give you 10 digits starting at 1 and ending at 10.
Yeah.
Or, yeah.
What do you think this 1:10 would do over here?
Would that do the same thing?
I think that does the same thing. Yeah. And if you're kind of unsure about it, just kind of play around with this in the terminal. So this you could do from a console. I realize I'm not sharing mine, but if you're you know, wanting to check this out, sequence 1:10, right? That gives me integer 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And 1:10 gives me the same exact thing, right? So like I said, there's oftentimes like many ways of doing the same thing in R, and it's not my job to try and tell you like every single possible way of doing it, but just know there are multiple ways of doing it. And you're welcome to, you know, develop your own style, whatever feels best for you. One interesting difference between this and for anyone that has worked in Python is that in R, we're inclusive of both of the endpoints, whereas in Python, it excludes the endpoint. So if you were to enter this command, yeah, that's right, we're looking at this screen now. Yeah, so if you were to enter this command in Python, it would stop at 9 and not include 10, just keep that in mind. Okay, and then you can kind of change the increment as well, is what this argument is doing over here. So we couldn't do that with the colon. So the sequence function, right, we have a little bit more customized, we can customize this a little bit more. So this would be like 1 starts with 1, right? And then it's going to go up by 2 to 3 and 5 and so on and so on. Then we know what this length argument does on here.
Yeah, I think it should give you 100 values between 10 and 20.
That's right. So this is going to take the interval and pick 100 values that are between 10 and 20. And so if you want to run that in a console and just kind of see what that output looks like, it's going to be long output, right? Because you've got 100 values, I think. Is that what the code says? Let's pick 100 of them. Yeah. So it starts at 10, it goes up to 20, and then it's going to divide that equidistant along the way.
You know how you might randomize that?
Yes. Then we know how you could randomize that. Let's see. So you could do like a sample would be a way of doing that. And we'll talk about how to like randomly pick numbers from a certain distribution. But if you do like a question mark sample, you'll see some help documentation on that. So that will pick a bunch of integers, and you just kind of need to kind of input what X is. So you can say like X is the first 100 integers, and then you can kind of randomly pick within them. Yeah.
Okay.
Okay, and so yeah, so that's a really nice way. I would say like this kind of sequence 10 to 20 length by 100. These are like useful things to do when you're plotting functions in R, because R works very numerically. It's not like a symbolic thing where it knows like how to plot the sine function. If you want to plot the sine function, you need to input like a bunch of things, and then it's going to calculate the output, and then it's going to plot each point individually. So if you want to get a nice plot of something, then what you need to do is just pick like a ton of points in between your initial point and your end point, and then plot them, and then sketch a curve that goes through them. So this is kind of a useful way of generating like the set of inputs that you're then going to plot in R. Okay, then down here, we have some nice ways of replicating values. So for example, if I want to just get like a vector that has the number 1 in it 500 times, I wouldn't want to type out 1 500 times, right? So that's where these sorts of things come in handy. So if we're kind of thinking about this piece over here, right? First of all, this is going to replicate the value. So 1, 3, right, in R, that's read as 1, 2, 3, right? Integers starting at 1, ending at 3. And then what do you think the times 3 option does at the end over here?
It repeats
The
it.
sequence 3 times.
Yeah, it repeats it 3 times. So we'd have 1, 2, 3.
Is that, does it repeat it as a nested list, or are all those values just independent variables within the list or the vector?
So this would be a vector that has 9 entries. So each one is separate. So like entry 1 is 1, entry 2 is 2, entry 3 is 3, entry 4 is now back to 1, and so on.
Okay.
Yeah, so what we're creating here, these are all vectors. So you want to think about these as individual entries in a vector. Okay. Let's kind of think about, what do you think the very last one down here would do? Skipping the one in the middle. So putting each equals 3.
Wouldn't it make it like 1, 1, 1, 2, 2, 2, 3, 3, 3?
Yep. 1, 1, 1. So 2, 2, 2, and then 3, 3, and 3. Okay, and so keep in mind that these vectors are like ordered lists. So there is like an inherent order to this. So we have the same numbers, they're just ordered differently now. Does anyone know what this thing would do? So this times is right telling us like how many times do we want to repeat the entries in this vector. This 1, 3, right? This is actually the same thing as like a vector 1, 2, 3. So what this is saying is here's the first entry in the vector that's telling me the times. So this is going to tell me I'm going to repeat this thing once. Then my next item, which is this over here, that's going to get repeated 2 times. And then this very last term over here, that's going to get repeated 3 times. So if you run this code, you should see 1 of these, 2 of these, and then 3 of those. These are pretty much the sequence and the replicate. These are kind of nice ways if you want to generate vectors that have certain patterns. And I kind of gave a little summary of things over here. Any questions about that? So these were all working with sorry, not integers. These were all working with decimals, right? We were working with 1, 2, 3 that happen to be integers, but they are stored as decimals. Yeah, and so then once you've got a couple of different vectors, you can always combine those two vectors together, provided they're the same data type. If you have different data types, then you may get an error in this if you're trying to create a vector. We're thinking about this first command over here. If I were to print out v1, what would I get?
A sequence of 1 through 5.
Get 1, 2, 3, 4, and 5. Okay, and then v2 is a vector of 3 entries, 1, 10, and 11. And then if I combine those two together, it's going to say 1, 2, 3, 4, 5, 1, 10, and 11, right? So it's going to create one vector that first has vector v1 and then is followed by vector v2, but it's all combined into one vector. So this sort of combining thing, if you did some statistics in R previously and you're doing like simulation type of techniques, like when you're like pooling two samples together and doing that sort of stuff, that's where this comes in handy. But this is a good chance, I think a lot of people here have had some experience in R and probably have kind of realized I've come across some problems at some point trying to do some stuff. So if there's anything you have a question on that I don't talk about here, you're welcome to ask. But like I said, R is so vast, I can't promise you I'll have the answer readily off the top of my head, but hopefully I can help you. Okay, so when it comes with categorical vectors, there is a data type which we can store as what's called a factor. So factor is actually a function, and I'll just say there were several built-in functions in R. Like R has been around for a while. That when it was first created, some inputs needed to be in the form of a factor. So this has been grandfathered in. I think some of these functions work just fine, whether these things are factors or not. But you really want to think about these factors as like different categories of one variable. And those categories might be indicated with a number, category 1, 2, 3, 4. It might be a letter, or it might be like descriptive of the category that it's describing. If we're working with an expression like this, okay, this is going to generate 1, 2, 3, 4, 5, 6, 3 times over. And in fact, let me just open up R and we can take a look at what that looks like. Let me know how the is this R window big enough to see what's going on? Yeah. So where am I in here? Let's see. Here we are. Yeah, so if I run this block of code here, it kind of creates this vector of all of these values, right? So we repeated 1, 2, 3, 4, 5, 6, 3 times over. But then it just notes that, right, we have 6 different levels here. Just level 1 is repeated 3 times. So it kind of condenses this and is just thinking about, well, how many different categories are in this vector? We can see we have 6 different categories, and it is not going to treat these like I can't sort it and stuff like this. So it's not treating 1 as being less than 2 as being less than 3. It's just the name of something. And you can see down here, it kind of goes the same way, that whether I have a character or a number, they're both being read the same way as really just a categorical description for one of the categories of a variable, for example. Okay, so I think I will have us just take a few minutes to like not listen to me and maybe say hi to some of your classmates. I'll just break us up into a breakout room. So you can imagine we're sitting in the little, 4-person tables in 4125. And I'll have you kind of think about with your groups. Oh, you're not looking at my screen. I'm going to go back into the PDF document. And let's work on the next question. I think it's question 5 on that document. So let's kind of apply some of these methods that we've talked about. So what we want to do is create a vector here that is called GRP, call it whatever you like. But this vector is going to have 2 levels. One level is A, one level is B. The first 7 values in this vector are going to be level A. And then this is not really the second 4, really, like the next 4 values are going to be B. So using these commands that we talked about, factor, replicate, sequence, I don't think you'll need the sequence one. There are different ways that you can do this, right? So I'm going to just break you up into some groups and you guys can chat about different ways that you could set up that vector. So breakout rooms. Let's see, we've got. So the rooms are going to have 4 or 3 people in them. And for those, is everyone familiar with how the breakout rooms work in Zoom? We'll see. So I just opened them up. So you probably should see something that says join a breakout room. So jump over there. You'll have a couple of classmates in there and I will just flip through and see if you guys have questions. Okay, recording is back. So does one group want to share what they did for this one?
Yeah, I just threw mine into the chat.
Ah, awesome. Let's see. So I'll write that down. So there are obviously different ways of doing this. Let me get rid of this. So let's see. So we've got a group. We're going to assign this. And then you've got C rep A 7 times. And then a rep, I'm guessing with a B. And then we see one thing that might be wrong with this. So what data type do you think this vector would be?
That's just a vector, right? You need the factor at the front.
That's right. So what you've got here is like a vector of characters. So it's reading A and B like the letters A and B. So that's fine. So you've got this vector now of characters that you would then want to convert into factor just using this factor. So just adding this here, or just adding another line of code, right? That then factors that previous vector would work. Any groups do it drastically different from this, or in a way that they think is really cool?
I did it 1 line at a time and then created a vector out of the 2 factors. So this is a little bit simpler.
Yeah, I mean, I guess that all depends. Yeah, like you could do create, this thing here and call this like F1, kind of like it was done above, and you can call this F2 and then combine those two together. Yeah, I mean, I think with like a lot of things, there's always this balance between trying to do like a whole lot in one command, or is it better to break it up into smaller steps? And I think in this case, like computationally, it wouldn't make a difference which way you do that. Sometimes you want to keep in mind that, especially if you're like doing a for loop that like nests 100,000 times, you might want to clean up things to make it efficient. But yeah, I think breaking this up into multiple steps wouldn't hurt that process at all in this case.
This keeps the vectors that you would use to store the two different subvectors out of memory. So it only has one vector in memory at the end
Yes,
instead of
that's
three.
true. That's right. That's right. And I think like in this case, the amount of memory is minimal, but if this were like a big, massive thing, that's right. And we were iterating this many times, these are things to consider, definitely. Yeah. That's right. Good point. That's a very good point. Okay, any other questions about that example or comments? Okay, so then that's about all I want to talk about as far as like creating vectors, pattern vectors. Next, we can talk about how we can extract parts of vectors. Then we'll kind of take this up another dimension to data frames, and then talk about how we can do the same thing with data frames. And so lots of ways that we can extract, or what are sometimes called slice things in R. And what's important here is when we're indexing vectors and arrays, in this case, indices start at 1 in R. Okay, for those that have done stuff in Python, right, things start at 0 in Python, which actually is extremely inconvenient in my point of view. Right, when you're working with a matrix, you always need to subtract 1 from what you really want to call it in Python, whereas in R, the first element is the first element, the second element is not 1, the second element is the second element. So I think that works pretty nicely. So if we want to kind of pull off an element, right, that is done by indicating what the number of the vector that you want to pull off, like the entry of the vector that you want to pull off. So for example, just putting like A1, this sequence A, which is 2, 4, 6, etc., this would just pull off for like the first entry of vector A. But oftentimes we want to pull off several entries of a vector, and sometimes we want that determined by maybe like a logical thing, right? Is this thing bigger than or equal to some number or something like that? So we can pull off multiple values at once just by indicating like a vector giving us the values that we want to pull off. So this would pull off the second, the fourth, and the sixth entry of the vector. Okay, not the number 2, 4, and 6, but what we're referring to are the second number in that vector, the fourth number in that vector, and so on. So this command over here, the 2, 4, 6, 8 would say, okay, this is the first entry. We're not going to pull off that one, but here's the second one. We're going to pull off that one. We're not going to pull off the third one. Here's the fourth one, and here's the sixth. So this would just give me an output of 4 and 6 and 12.
Wouldn't it be 4, 8, 12?
Yes, thank you. That was an example of one of my many planned errors this semester. That's right. So far you've passed. Thank you. Yes, I highlighted 8, thanks. Yeah, and we can do a similar sort of operation by by excluding certain things by just putting a minus sign here. So this would be everything except for to the second, the fourth, and the sixth entry. So it would be everything that I haven't highlighted up top. And so this line is doing a couple of different things. Whoops, we stopped at 6 here. Right, so this 3:6, right, that's telling me all of the integers starting at 3 and ending at 6. And so that's telling me which entries, the minus sign in front of that's telling me these are the entries you want to exclude, right? So this would therefore pull off the first two entries. Then it's going to skip 3, 4, 5, and 6. I think I'm doing this right. And then that leaves the 14 and the 16 left over. So, right, different ways of combining these different techniques for extracting values out from the vector. Any questions? Okay, so then we've got various functions again. I can't list all of them in R, so these are just some that we'll use quite frequently this semester that you may have already used quite a bit. And so in this case, X is representing a vector of stuff. Some of these functions wouldn't work if X is not a numeric vector, right? So we can't take the mean and variance and standard deviation of characters and things like this. We're going to assume here we're dealing with like a numeric vector X. These are various types of functions. The length function for X, by length here, it's going to tell us like how many, how long is the vector? I guess that's what I'm trying to say here, right? How many entries are in the vector? So that sometimes is like what we might set as like the sample size. That's what I mean by X. That's oftentimes how we can pull off how large is our sample, something like that. But R is not trying to make things complicated for you. So for example, the sum of X is not doing anything other than summing up all of the values in X. So the function name is trying to be very descriptive of what it's accomplishing. And so if you're ever out there thinking, I would like to do some sort of operation on X, probably that function already exists, so you may not have to like write out, add up all of the things in X and then divide by N, right? So clearly we could come up with like this mean function, right, using the previous two things, but we don't need to because someone already defined the mean function. Okay, so I think that we can, unless there's some questions about these functions, I think I will kind of just let you play around with this. But one kind of new thing that we see over here is this REXP, and we'll get into distributions very next thing. But this R is telling us to randomly select 100 is telling us how many values from exponential distribution. And in this case, it's assuming that the mean of that distribution is 1. If you had some other mean, then you would enter that after the 100. So if you all ran this code, unless there's some miracle, right, we would all get slightly different outputs from these functions because we all would be working with a slightly different x. For those that might be wondering, this IID means like identical and independently picked from the same distribution. So it's just repeatedly picking values independently from the same distribution. But any questions about these functions that you've had in the past that you think might be worth clarifying here? Does anyone know what summary does?
It automatically runs several of those functions.
That's right. So that's always like a good start. It's going to pop out like a 5-number summary in addition to the mean. And I think it also gives you a standard deviation possibly. Yeah. Okay, yeah. And again, if you're ever unsure what these things do, right, just put question mark name in the console and you'll get help documentation on that function. Okay, so next up are these various functions that either calculate probabilities or randomly generate these different distributions. And so there's like a whole bunch in R. If you're curious which distributions by default are in the base package, then you can do a question mark distributions. But generally how it works is P is the prefix for CDF, right? Meaning at most Q. Whereas D, if we have a prefix of D, it's telling us the probability of exactly X. So those are two things that you want to keep distinct there, but they're kind of doing similar things. They're going to calculate what is the probability that X is equal to or less than or equal to something if it were picked out of some specified distribution. The R is what we just talked about. That means randomly pick things from this distribution. And the Q is doing the inverse CDF. So in other words, it's calculating quantiles, percentiles. So it's kind of doing the inverse of what is above. So that's kind of the default about how R works, is you use a P, a Q, a D, or an R as like the prefix. Then you indicate the distribution that X is from, and then you indicate some parameters for that distribution and some indicated value of X that you might be interested in. Okay, so let's take a look at some examples. So these were some from when we learned this in 3382. So these are some statistical questions that we can answer using these functions. So maybe let's kind of just chat about one of them together, and then I'd like you guys to maybe think about some of these others, but let's do B, which is this. We're looking at a distribution for IQ scores. And so IQ scores are normally distributed, and we've got a mean of 100 with a standard deviation of 16. So we'll assume like this is the population. Okay, so we could write that as X is normally distributed, right? Mean 100, standard deviation 16. And so this is saying, well, what is the probability that someone would have an IQ score that is between 75 and 100? So in this case, the distribution that I'm working with is normal. So that distribution qualifier that I'm going to need in my function in this case is norm. And again, if you're not sure what the kind of abbreviation for that distribution is, and then that's where that question mark distributions might come in handy. This is probably like the most commonly used distribution would be the normal distribution, certainly in statistics. So if I were to do something like D norm is equal to 75, 116. So kind of first is going to go in some value for X. And then after that comes in however many parameters we need to establish what the distribution is. So for normal distribution, there are two parameters, the mean and the standard deviation. If I were to enter this into R, what would I get?
Uh, 0.0073.
Is that what you got?
Yeah. I don't know if it's right, but that's what I got.
And what would that tell us?
The chance of being in that interval is 7%, right? About that's 0.7%. I can do my math critically.
Yeah, so we want to interpret that as like a percentage, right? A proportion. This is really telling us like what is the probability that someone has an IQ score that is about 75. I'm being really rough with my interpretation here, but keep in mind this is really what we would use in some sense to tell us like what is the probability that X is exactly a certain value. And so when you're working with continuous random variable like a normal distribution, keep in mind that like nobody really has an IQ of exactly 75. If you were to think about like measuring heights, like the probability that a random variable equals any one specific value is going to be 0, because you're thinking about areas, right? So really the picture here is we have some normal distribution that's centered at 100. Here's the value 75. If I'm thinking about like what's the probability that someone is between 100 or has an IQ between 100 and 75, not drawn to scale here, right? I would essentially be wanting to calculate this area underneath the normal distribution. This function over here is telling me the height on this graph over here. Okay, which is really not all that helpful when we're working with a continuous distribution. Just keep that in mind that the D prefix, really we're just going to be using that if we have that the D is kind of like a discrete. You can almost think about it like that. It has some interpretation when we're working with a discrete random variable, because then we can get, you know, X is exactly a certain value, but not with a continuous distribution here. So instead of a D here, I'm going to put a P And this would tell me what is the probability that X is less than or equal to 75. So that's actually telling me the stuff in the tail to the left of 75. So how can I use this information to actually answer this question over here?
Subtract it from 0.5.
Yeah, that's right. So I know that to the below 100, right, would be half of the area. And then if I subtract off this stuff in green, then what's going to be left over is just that slice in red. So I'll let you kind of think about these with your classmates. This will be a little bit trickier because you're going to need to think about what distribution might make sense to kind of model the situation. And it may have been a while since you've taken some probability. You may not have had a course in probability. So we'll see how this goes. You don't need to do them in the order that I've asked them. I imagine A might be the trickier one. But just to kind of help you get going, right, these are discrete distributions where this is going to be a continuous distribution. So in A and B, we're counting things like how many TVs did they sell on a certain day. You're not going to get a decimal for that. The same with C, you're counting how many people actually have the flu. Whereas D, you're measuring the amount of time between calls. That could be any sort of decimal value. We're not just dealing with integers. So I will re-scramble you up again, just so you can say hi to somebody else, and give you a chance to kind of talk about some of these, and then we'll come back together. So I'll plan for maybe 5 minutes of talking about this. So we'll plan to come back at about like 1:33, something like that. Let me open up breakout rooms, reshuffling. Okay. The room should be open. If you guys have questions in your room, there's a button that says ask the instructor. You're welcome to hit that and I'll drop in. We'll kind of resume recording. Okay, so let's kind of just touch base with how these went. Let me share my screen. And so I think kind of like the larger picture here when you're answering any of these questions, I think like, yeah, like step one might be identifying, is it continuous versus discrete? But then like R is not going to tell you what distribution that you would want to use. So that's something you would need to think about first. So I was chatting with one group who had binomial distribution over here, which is a reasonable distribution to pick. Right, we can see down here that took some of the fun out of it, but we're told like this is exponentially distributed. Did anybody know what distribution A would use?
Poisson.
Yeah, very good. So this would be a Poisson distribution. That's right. Then the question is, okay, so in part A, we've got X. This is a Poisson distribution, and we're told that the average Poisson distributions just have one parameter, which is lambda, which is like the average value. So then the issue is, all right, so this is asking me, what is the probability that they sell, right, exactly 9 TVs? So the reason why this isn't binomial, right, is we don't have like a fixed set of trials. We don't know what the probability of a success is on any one trial or anything like that. But we know how many TVs they sell on average, and we're trying to calculate, well, what is the likelihood that they sell a certain number of? So it's like, okay, let me identify what distribution is involved. That's a Poisson distribution. Okay, then let me identify what is the probability that I'm asked to calculate. And kind of those two questions are going to help me identify which function am I using above, right? Because I'm using the Poisson distribution, that helps me identify which distribution. And if you didn't know what to call Poisson, then this will help you kind of call that out. And the next thing is, well, what's the prefix that I am going to use? So for the group that kind of used Poisson here, what was the prefix? Are we going to use a P, Q, D, or an R here?
I use D.
That's right, because we want to know exactly 9. So that's correct. So we're going to put a D here. And then we put 9 and 5. Okay, the 9 is what we want X to be. And then after that would come whatever number of parameters we need to identify a Poisson distribution. That just has one parameter there. And so if you've never used these functions before, then I would definitely encourage you just to use the help documentation. They make it really clear about first enter this, then enter that, then enter that, and so on. Yeah, and so in C, it's pretty similar. We want to know what is the probability that X has exactly, that we have exactly 4 successes. And in this case, right, success is not necessarily a good thing. But here we've got that X is binomial distribution. And we know that we've got 25 trials. So that's our value for N. And each time the probability of a success of that person having the flu is 4%. And so the binomial distribution is binom. We want to know what is the probability that we have exactly for out of 25, where each probability of success is 0.04. So when you enter these in, you could say like N equals 25, probs equals 0.04, or you don't necessarily need to type those in. You can just enter the values. Okay, and then in D, we're told that this is exponentially distributed, and they are getting an average of 1 call every 2 minutes. So the parameter here would be lambda is 1 over the mean. So the parameter here is 1/2, right? And this one is asking us what's the, for what value of X, let's put it this way. Here's my exponential distribution. We're trying to find what value of X, right, the 99th percentile, has an area of 0.99 below it. So we've got the X distribution, and in this case, right, we want to kind of do the inverse CDF. So we want to use a quantile function. So we're going to use a prefix of a Q before that. And then the very first thing we enter is the probability 0.99. So we're going to put a Q before that because we're doing the quantile for the exponential. The quantile that we want to find is the 99th. And then our parameter for the exponential is 1/2. We just write that as a decimal. Okay, trying to knock some cobwebs off of your head if it's been a while since you've thought about these probabilities. Any questions about that? Okay, So we're just about hitting our time limit. We hit our time limit. So I will pick up at this point over here talking about data frames, but basically we now just have a second dimension that we can slice things. So the way that we extracted vectors, we now just have 2 dimensions that we can identify depending on which rows and which columns we want to subset out from this data frame. But we'll pick up with this and start to talk about generating plots and doing some exploratory data analysis in our next week. And then we'll be ready to kind of start talking about doing some regression. Cool. Okay. Well, week 1 of remote learning in regression done. 1 more week of online learning, and then I will see you all back in class in a couple of weeks. But have a nice weekend, and the homework assignment is up, so feel free to get going on that. And if you have any questions on it, just let me know.
Thank you.
Yep.
See
Take
you
care,
later.
everyone.
Thank you.
You.